All right, so today we're going to be going over Chapter 7 for Principles of Statistics. Chapter 7 has 3 different lessons in it, and we'll hopefully go through all of them now, at least a few problems. These are all problems that you should see in your homework or on the Hawks Learning System. So some of this stuff might be a little bit familiar to you already. All right, so let's look at Lesson 1 of Chapter 7, which is an introduction to the central limit theorem. So before we dive into the problems that we need to do with the central limit theorem, it's important that we know what the central limit theorem is. And so let's talk a little bit about what the main parts of the central limit theorem are, the criteria that we follow if we're using the central limit theorem. So the central limit theorem says that the mean of sampling distribution of sample means coincides with the population mean. So basically what this is saying is when we're using the central limit theorem, when we've talked about means in the past, where we've talked about you can have a mean for a sample or a mean for a population, in this case, they're the same. They're going to be the same number. There's no way of they coincide. There's no way to decipher between the two. We use the same mean for both the population and the sample, and that's a little bit different than you've done in some of the other chapters. So do make note of that. So the standard deviation of a sampling distribution of sample means coincides with the standard deviation of the population divided by the square root of the sample size. Okay, so that definition I took out of the book, it's a bit wordy, so I'm going to try and explain it a little bit differently here. So what this is basically saying is that, so right here you can see we have like the standard deviation. Let me do a markup here. Okay, so we have like why is my pen not working? Okay, so if you can see in that second equation that I have there, the sigma, which is like the little O looking Greek letter, we can see 2 of them. Now the one with the X bar beside it, that means that it's referring to the sample. Now the one without the X beside it, which, see my pen will work now. Okay, so here's what I was talking about. So the one with the bar beside it is the one that is referring to the sample. Now, this one is referring to your population, and this n is referring to your sample size. So the total number of people that you're sampling is equal to your n. Now, your standard deviation for the population will be given to you in the problem, and these criteria should make a little bit more sense whenever we actually dive into the problems. I know sometimes it's hard to kind of understand it without looking at it from a math point of view, because right now it's just words on a page, but we will get there in a second. So the shape of a sampling distribution, let's look at the next one for now. The shape of a sampling distribution of sample means approaches that of a normal distribution as the sample size increases. So what I put in parentheses again, because I took that definition from the book, it's a little bit wordy. The bigger the sample size, the closer it is to the normal distribution. So we're not using a normal distribution like we discussed in chapter 6, I believe, and maybe chapter 5. We're just approximating it, trying to get close to a normal distribution, but it's not exactly a normal distribution. So the central limit theorem isn't following a normal distribution to the t. Finally, the last criteria is that you have to have 30 or more in the sample to use the central limit theorem. So if you have anything less than 30, the central limit theorem can't apply. All right. So here we have just a few statements that these were taken directly out of the homework, and you should be able to answer whether they're true or false regarding, or if we refer back to the definitions we have here. So the first question says, decide if the statement is true or false. A sampling distribution of sample means has a mean equal to the population mean divided by the sample size. So what we're saying is that the Sampling distribution, sample mean. Okay, so mean is used by mu. And remember, mu for a sample mean, we use the little x bar because the x bar refers to a sample rather than a population. So what we're saying here is sample mean is equal to a population mean, so that's just mu without the x bar, divided by the sample size, and sample size is denoted by n. So let's go back to our formulas that we were given here, and we're given these two. And what we wrote out here from what this problem is saying, none of the formulas match here. Our sample mean and our population mean are the same. They're equal in the central limit theorem. So this answer is false. We only use the standard deviation to divide by the standard deviation of the population by the standard deviation or square root of the sample size. All right, so another question is, can a normal approximation be used for a sampling distribution of a sample means from a population with a mean of 44, a standard deviation of 8, and an n of 49? So let's go back to our criteria here. So we have to follow all these things to be considered, I guess, to be able to apply the central limit theorem. Now, we're not really talking about the standard deviation calculations or if what the mean is equal to in this problem. So really the only thing that would apply here is that we must have at least 30 or more in the sample. If we go back, we remember that n is referring to our sample size, and n here is 49. So since 49 is greater than 30, yes, we can use it because the mean is at least 30. So those are just a few questions that refer to the criteria that you can use to apply the central limit theorem. And Hawk's Learning does ask you some questions like those, so I wanted to go over them. Now let's start digging more into the math. The first few questions are pretty simple. They might seem like something you would want to overthink because usually when we think of math, we think of something complicated, or at least most of us do. Let's see here. So find the mean of a sampling distribution of sample means using the given information. So round to one decimal place if necessary. So we're looking for the sample mean. So remember, sample mean is denoted by mu with an x bar. And if we go back to our formulas, scroll back here. Again, we can keep referring back to this if you need to look at the criteria again. Now, our mean sample, our mean of the sample and our mean of the population are equal. So, all right, so this is equal to just our population mean. Now, in this case, we're just given our mu, but if our mu is equal to our mu is the letter, by the way, in case you're not sure. Mu is that Greek letter that we're using for the mean. If these two are equal, then the 51, that is for mu, would be equal to the sample as well. So again, like I said, this is rather simple compared to what we might think it is, but really, we are just approximating the sample mean, again, with this formula here. All right, so here's more of a math-related one. It's a two-step problem. So on a study on the latest fad diet claimed that the amounts of weight loss by all people on this diet had a mean of 20 pounds and a standard deviation of 3.4 pounds. So question 1 says if a sampling distribution is created using samples of the amounts of weights lost by 97 people on this diet, what would the mean of the sampling distribution of sample means? Round to 2 decimal places if necessary. So again, this question sounds really wordy, but it's really just asking, when it says the sampling distribution of sample means, it's just asking what your mean would be. And in this case, we've used the formula before where the mean of the population and the mean of the sample in a central limit theorem, they're equal. So all we have to do is find the mean that they give us in our problem, and that will be our answer. So if we read up here, it says the mean is 20 pounds, and so that is our answer. All right. Now, step 2 says, if a sampling distribution is created using samples of the amounts of weight lost by 97 people on this diet, what would the standard deviation of sampling distribution of sample means be? Okay, so let's look here and remember referring back to our formulas that we went over when we discussed the criteria in the beginning. To find the standard deviation of a sample, remember the x bar is referring to the standard deviation of the sample, we use the standard deviation, denoted by the sigma, of the population over the square root of n, and n is our total and entire sample size. So what we have to do really is just plug in this information to get our standard deviation for the sample. So in the problem, we are told that the standard deviation is 3.4 pounds, so that's going to go on top. And here in the second part of this problem, we're said that 97 people are trying this diet, which that is going to be our total sample size. So 3.4 over the square root of 97 should give us our answer. And if we put that in our calculators, which you should just make sure that you divide and include a square root, you should get roughly 0.35. Now you'd have to round it off. You're going to get a long decimal, but it says round to 2 decimal places. So if you round it, you should get to 0.35. Okay, so find the standard deviation of the sampling distribution of sample means using the given information. Again, this is very similar to the last problem that we just did in step 2, because we took this formula to find our sample's standard deviation. So again, here is the formula we're going to use. And always I try to reiterate that the x bar by the sigma refers to your sample. If it doesn't have a x bar beside it, it's referring to your population. So here we're given the information straight up, so all we have to do is plug it in. We don't have to decipher through a word problem. So our standard deviation here, we got a 6. We divide by the square root of n. They tell us n is 64. Now, if you do this problem, and work that out, you should get 0.75. Again, you'll probably get a long number, but you're rounding to 2 decimal places. Okay, so what I kind of want to talk about here is a common mistake I see, because I don't want people to make this mistake, because it's just a very common error. So a lot of students will just write 6 when it says what's the standard deviation. And that's wrong, because that's the standard deviation for the population. What we're doing is we're wanting the standard deviation for the sample, so there's a formula that you do have to plug into. So I just want to remind you that if you're asked to find the standard deviation of a sampling distribution of sample means, you should not just plug in the standard deviation you're given as your final answer. You are going to have to use this formula. All right. So that's all I really have for 7.1. Let's go ahead and move on to 7.2. So lesson 7.2 is the central limit theorem with means. So we're going to be looking at problems that specifically have to do with the mean. All right, so for this lesson, we can utilize the normal CDF function in the calculator, and it will make your life a lot easier. You won't have to work out as much by hand, so I would suggest using this. Here's the directions for the steps of how to use it on a TI-84, and it's very similar for a TI-83 Texas Instrument calculator. If you have other calculators, they should do this too, as long as they're a scientific calculator. The process might just be slightly different. So I'm going to explain in these problems how to plug them into your calculator, so that hopefully that will help you to understand. Okay, so let's read through this problem. A product manager at a wall clock company wants to test their new wall clocks. It's a mouthful. New wall clocks. The designer claims they have a mean life of 16 years with a standard deviation of 3 years. If the claim is true, in a sample of 37 wall clocks, what is the probability that the mean clock life will be greater than 16.7 years? And we're rounding to 4 places. Okay, so as I said, we can use the normal CDF function in this for these type of problems of the central limit theorem with means. And again, I want to reiterate that remember that 3 is not just the standard deviation you're going to plug into your calculator, because that is the standard deviation for the population. We are wanting to find the standard deviation for the sample. So we have to use this formula here. So if you go into your normal CDF function on your calculator doing these steps, you're going to go to your distribution with second var stats, select your normal CDF and press enter. You'll have a lower bound, an upper bound, a mean, and you should have a place for standard deviation. So you're going to need 4 things to plug in. So in this one, I already have listed here what goes in what category. So like I said, you're going to have a lower, an upper, standard deviation, and a mean. So now I'm going to explain how I got those numbers. So first off, let's kind of go through this problem, see what we know. Okay, so here they're saying that the mean, 16 years, the standard deviation of 3 years. Remember, that's just the standard deviation with population and not the sample. We're looking at a sample of 37, so that's like our n value. And our mean clock life will be greater. We want to know if the probability that it would be greater than 16.7 years. Okay, so for lower, that's your lower bound. That is the bottom number that you can have to follow this problem. So in this case, we want everything that would be greater than 16.7. So if we're like looking and thinking of a number line like this, 16.7, we'll just say it's here, and you have all these numbers below 16.7, all these numbers greater than 16.7. Since it says we wouldn't be greater than 16.7 years, we want everything above that as far as we can go, which means that our lower bound is going to be 16.7 because that's the smallest value we can have. We want everything bigger than that. And since we want everything bigger than that, we could say that we could keep going until infinity, like whatever number is bigger. Now, the way that we approximate infinity, which we can recall from previous chapters, is that you do 1 times 10 to the 99th. That is our way of approximating infinity. So what you would do in your calculator is just do 1 and then the times button and then do 10, and you can use your little caret and you're going to put it to the 99th. That's how we approximate infinity in the calculator. Okay, next we have our standard deviation. And in your calculator, it will just pop up like this, but really what it's wanting you to plug in for these type of problems is this. So like I said, remember that it's not just 3. It says right here, standard deviation is 3 years. But remember, that's what we've got to plug in because that's for your sample. So using this formula, what you would do is we said, I'm just going to write this out. All right, so we said our standard deviation is 3 over our total sample size. And we set our sample size here, and the problem is 37. So that is what's going to go right here. Now I have it in the decimal format because in your calculator, that's that's just what I like to put in. I like to calculate it out like this and then get the long decimal. And if I do it that way, then I can make sure, like my calculator just automatically converts it into a decimal when I use the normal CDF function. Your calculator might not do that, and it shouldn't matter which way you do it as long as you're doing it correctly, typing in the right parentheses and separating it from like your lower bound, your upper bound, and those sorts of things because if you don't, then you might get the wrong answer. I put it into a decimal because I think it's easier to just type straight in and not have to worry about making sure your parentheses are in the right place. All right, so the final thing that we have to enter is our mean. And in this case, our mean is 16 because that's told to us directly in the problem. Up here, right here, the mean is 16 years. And remember, the mean of the sample and the mean of the population are the same, so we don't have to do any calculations like we did up here for the standard deviation. Now, when you plug that all into your calculator, the lower bound, the upper bound, the standard deviation, and the mean, you should get 0.0778. Now, with all of these problems in chapter 7, you're going to get some kind of decimal answer, and that's okay. You're going to want to round it to 4 places, almost always in Hawks. And so if you're getting a number like way over 1, it's probably wrong. You probably messed something up because you should be getting a small decimal. So that's a good way to kind of check your work to make sure you're on the right path. Okay, next problem we have is very similar, but this one, we're looking at less than. Last problem we had, we wanted something greater than 16.7 years. Now we want something less than $35.2. So the cost of 5 gallons of ice cream has a variance of 49 with a mean of $37 during the summer. What's the probability that the sample mean would be less than $35.2 if a sample of 77 5-gallon pails is randomly selected? Again, round to 4 places. So we can use normal CDF for this, like the steps in the last slide where we had a lower bound, upper bound, mean, and standard deviation. Again, this should be different, that's my fault. Remember that the standard deviation that you're given is not the one you're going to put in the calculator, since we're approximating using the central limit theorem. So in this problem, we have to find our lower bound, our upper bound, our standard deviation, and our mean. So first off, we want everything less than $35.2. So again, if we want to visualize this, what we can do is we have 35.2 here, all the numbers bigger than it, all the numbers smaller than it. We want everything going this way because we want everything less than. So we can keep going as far to the left as we want. We can go all the way to negative infinity if we want. The highest value that we can have, according to this problem, is 35.2. That is why 35.2 is our upper bound. Now, if we can have everything less than 35.2, that is why we can have negative infinity. So, like in the last problem where your upper bound was positive infinity here, we can do the same thing, but in this case, we want it to be negative because we want everything smaller. So we approximate negative infinity by -1 times 10 to the 99th. All right, next, standard deviation again. We're going to follow the same formula. We're looking for the standard deviation of the sample, not of the population. So we've got to figure out what to plug into our handy dandy formula. All right. Now in this problem, we can easily see our n value. We're sampling 77, so 77 goes here, but nowhere in this problem do I see standard deviation stated directly. If we look, we have a variance stated, a variance of 49. Now, a good thing to remember is that variance, I'm going to abbreviate it like that, VAR, it's equal to your standard deviation squared. So that's like an exponent 2. It's not going to be like the number times 2. It's going to be the exponent 2 is going to be the same. It's also you could write it as your standard deviation is equal to the square root of your variance. Now, a hard concept that sometimes people have a hard time understanding is that a square root and an exponent are the same. They're like kind of like opposites. Variance equals standard deviation squared, and standard deviation equals the square root of the variance. So in this case, we're given variance, so we want to find the standard deviation. To get the standard deviation, what we're going to have to do is take the square root of 49, because 49 is our variance, so if we just plug that in, we can get our standard deviation. So 49 divided by, 49 with the square root of it is 7. If you want to see how that works with going from how variance is equal to your standard deviation squared, if you square 7, so your calculator should have like a little arrow, like a little button key that you can arrow up, or a square exponent, and if you do that, you should get 49. They should be equal to each other. But anyways, in this case, we are wanting the 7 because that is going to be our standard deviation. All right, so we have 7 to plug in here. Okay, so if we do that in our calculator, what you should get is this number here. And I just double checked it, and that should be what you get. So that's how we plug those in. And then finally, we need to go over how to get the mean. Remember, we do not have to do a crazy formula for the mean. We can just plug the mean straight in because the mean of the sample is equal to the mean of a population. So in this problem, we're told that the mean is 37, which is why I put 37 right there, and that is what you plug in to your mean. All right. So if you plug those in your calculator, you should get 0.0120, and that should be your final answer. All right, let's move on. Again, these are similar. We're doing still normal CDF, but we have to take a slightly different approach with this problem because it says differ from the population mean by less than. Those are the key words here. If you see the words differ, you're going to have to take a slightly different approach than if you just saw greater than or less than. So here, we still are using normal CDF, so we're still going to have a lower bound, an upper bound, a standard deviation, and a mean. Here is what the answers are, but I'm going to explain how I got them here and what we have to do differently since it's different. So first off, let's go over what we know. So the mean lifetime of a tire is 42. So the mean is 42. And we have a variance of 49. So we'll have to do like we did in the last problem where we were given variance. We had to take the square root of it to get our standard deviation. So let's go ahead and do that now. So if I take the square root of 49, you should get 7. So 7 should be our standard deviation in this problem. So we're sampling 145 tires, and we want the probability that it will differ by less than 0.08 months. So now we figure out what to plug in where. Let's start with our mean and our standard deviation because those are the easiest to come up with in these type of problems. Remember, your mean for your sample is equal to your mean for the population. So all we have to do is take the mean that we are given in the problem and put it in, and that's what we're going to plug in our normal CDF function. To get our standard deviation, we're just going to go back to this formula once again. And in this case, we are told, or we calculated the variance, 49, to get the standard deviation of 7 over the square root of n. N is how much we've sampled, which is 145. And if you do that, you should get a decimal looking something like this. So that's how you get your sample, your sample standard deviation, your sample mean. Now, if we want to talk about your lower bound and your upper bound, this is where things start to differ than in the just greater than and less than problems that we previously did. So if you see the words differ, this is what you're going to do. Now we want to say that, let me erase all this stuff up here so you don't get confused. Okay, so we want to say differ the population mean by less than 0.8 months. What that means is, let's draw a number line out to visualize this again. So our mean that we were given was 42. So let's put 42 here in the middle of the number line. And the values that we're looking for, we can either go plus 0.8 months towards the positive side or plus 0.8 months towards the negative side. And that's because we're saying that we want the population mean to differ, by less than 0.8 months. So you can go 0.8 months one way towards the more positive side, or 0.8 months the opposite way, more towards the negative side. So if I did plus 0.8, I get 42.8. If I subtract 0.8, I get 41.2. All right, and that's where I got those numbers. So obviously, whichever one is smaller here is going to be your lower bound, and then whichever one is bigger is going to be your upper bound. So that's what I was meaning by whenever you have to take a slightly different approach with less than and greater than, or different approach than whenever it just says less than or greater than. If it says differ, you will not have to use negative infinity or positive infinity. You should get two values that you're going to have to add or subtract from the mean that you're given. Okay, so if you put those in your calculator using the normal CDF function, you should get 0.88324. Okay, the final type of problem that I want to go over for this chapter is similar to what we just did. This one says differ from the population mean by more than 0.6 gallons. So last problem, we discussed differ less than 0.8 months. Here we're saying more than, and that's the key word. More than is probably the hardest type of problem because it has the most additional steps. It's kind of like in some of the different problems, like more than is, we're looking at a number line. More than is like towards the right. So if it's like 100, this is 0. So more than is towards the right. So like thinking back to chapter 5 or chapter 6 when we started doing z-scores, and you had to take the opposite when you're going towards the right side. It's kind of the same to more than. What I've learned in statistics is a lot of things that are more than or towards the right side, there's usually additional steps. So if you see a more than, your mind should kind of think like, oh, there's probably going to be more additional steps than if it's just a less than or a greater than problem. Okay, so let's look at the additional steps that we have to go over. All right. Okay, so using our normal CDF function, again, we have to have our lower bound, our upper bound, our mean, and our standard deviation. Again, let's go find our mean and standard deviation since those are the easiest ones to find first. Remember that our mean, we don't have to do any formula calculations for it. It's just what is given to us in the problem. In this case, it says the mean is 87 gallons. That's why I put 87 as our mean. Our standard deviation, again, we're going back to this formula, which hopefully you can remember by now. And what we're going to do is plug straight in what we know. Remember, don't just plug in 6 as your standard deviation. You do have to do this formula. So 6 divided by the square root of n. We are sampling how many? Okay, 41 race cars. Okay, we're sampling 41. And if you do this, you should get a fraction the fraction should be roughly equal to this number over here. And I put the dots if it's a really long decimal. That way you just know that I didn't round it off, it just keeps continuing. Now, our lower bound and our upper bound. Just like in the last problem, when this one says differ from the population mean, we're going to have to add and subtract again. So let's look back here to our number line. So I'm going to put our mean right here in the middle, and our mean in this case was 87 gallons. So we're going to say differ from the mean by 0.6 gallons. So this means that you could have a little bit of extra gallons of gas, like 0.6 of it, or you could have a little bit less gas. You could have a little bit too much, but nothing too extreme. You're kind of staying within a range. But I like to kind of think of these problems that are differ is you're going to have a range. Your numbers are going to have to fall between 2 points on the number line, so like here and here. Whereas with just greater than or less than, and you have negative infinity or positive infinity, you're not really having numbers fall within a range. They can fall in this whole slew of all these negatives or all these positive numbers. So with differ than, you're going to have 2 points. So if we add 0.6, since that's how much it says that the mean differs by, or can differ by, we get 87.6. So that would be like this little dot here. If we subtract 0.6 from 87 and go towards the more negative side, we would get 86.4. So these are like the ranges that you can have. These numbers can fall in between. So like I said in the last problem, if it's differ than, you're not going to use 1e99 as negative infinity, or 1e, or yeah, I don't know if I said that right, 1e99 for positive infinity, or negative 1e99 for negative infinity. You're going to have 2 number points. And so that's why I plug those in as our lower and our upper bound. Whichever one's smaller just goes in your lower bound, obviously. And when you calculate that, you should get this right here. So 0.47803 ... There's a long decimal. Now, in the last problem with the more than, after we plug those in, that's the only additional step we had to take. But with less than, that's the only additional step we had to take. With more than, what we have to do is subtract it from 1, like kind of going back to the complements rule that has been discussed throughout the chapters in this book. And you subtract from 1 always to get your final answer. Okay, so your final answer ends up being that number 0.5220 when you subtract that out. So with differ from the mean, greater than, or by more than, you do always have to subtract the answer you get from norm CDF from 1. Sometimes I'll see it written out as something like this. So like your 1 minus your norm CDF. And you might be able to input that in your calculator that way too. I usually just get my norm CDF and then subtract it from 1 so I can make sure it came out right. But however you do it, it doesn't really matter as long as you get the right answer. Okay. Those are the 4 main types of problems that you'll see in 7.2. Let's go ahead and move on to the last section in this chapter.